Okay, let's go through this one now. B2. A body moves with simple harmonic motion. How will the acceleration vary? Well, I think a graph actually could show it.
I think it equals. I think.
Well, if I put distance here and acceleration here in meters per second squared, in meters, what will happen is if you increase the distance, the acceleration will increase. Yeah. In fact, it looks like this.
So as the acceleration goes far from the
Increases. Yeah, and then when it's at the equilibrium, it's zero. Yeah. Yeah. So you could say that acceleration will increase, then decrease. Yeah.
I remember the acceleration will be zero
At the equilibrium, yeah.
So I think mass decrease then gets there.
And then decelerate. Yeah, I don't know. The graph really says it all. Okay, the B part. You have a mass of 0.15 kilograms and the extension is 5.64 times 10 to the minus 2, so that's actually centimeters. What's the spring constant? Sorry, Louise, can I go down? Yep. So, the spring constant, what formula will, the spring is like this.
We use Kx.
Yeah, you can say F equals Kx. Now what's the F here?
0.51.
Yeah, it's mg. And then here's the F. So you get mg equals K delta X. So that means K equals mg over delta X. Well, I'll check. What did you get? 26 I have. Now maybe I typed it in wrong. Maybe I should believe you. You do as well? Something went wrong for you, who? That's okay. We all make mistakes. 26.09 newtons per meter. Okay. Part 2. The mass is then pulled down a distance and then starts to oscillate. What's the time? Well, in fact, the formula for the time is in the formula book. I think it's 2 pi root k over m, isn't it? Actually, I always mix it up. 2 pi root m over k, you sure?
Yes.
Yeah. 2 pi root m over k. So that would be 2 pi root 0.15 over 26.09. Not so difficult really. 2 pi root 0.15 over my previous answer, and I get 0.476 seconds.
Now, I have a question.
Yes.
Because my constant is wrong, so the rest of answers.
I might still give you the marks.
The full mark.
I think so.
Full mark.
Maybe.
Wow.
Maybe. See how I feel.
If you feel bad,
If I feel bad, maybe I give you most of the marks. I don't know. It's complicated because it depends on many things. But the most important thing is you continue with the question, even if you feel your answer is wrong. Yeah.
if I have all the formulas right.
Yes, of course, yes. This gets marks, yes. Yeah. Okay, can we go to the next part? Oh, so easy. If you remember the formula. What's the formula for frequency? 1 over t. And what's the unit?
100
Hertz, yeah.
per second.
Yeah. 2.099 hertz. Okay. Now, does anybody remember the formula for the maximum velocity?
Omega or
Yeah, A omega, I think. Yeah.
the unit is A omega.
Yeah. Well, it's x omega when x is the maximum. Now, we don't know omega, but we have a formula for omega. What's the formula for omega?
2 pi over t.
Yeah, 2 pi over t. So, I suppose, what's the formula for 1 over t? What's 1 over t?
Frequency.
Frequency. So if you wanted to, you could actually write the formula like this, 2 pi AF, because you know the F, and you know the A is in the question. What's the A? 2.56 times 10 to the power of minus 2.
Unit plus 5.64.
No, actually not. No, just the distance which has been pulled is what you need.
But the question is that it says cause the spring to extend by.
Yeah, but the spring's not moving. The amplitude is the distance it moves from the equilibrium, not the total extension. So maybe just to clear this up here on the side here, if you have a spring here, and this is the extension, and it's not moving, okay, it's not moving, the amplitude is 0. And then if you move the spring to here, and it starts going up and down like this, then the amplitude is this distance here. Okay.
Question.
Yes.
How we need to find out the difference? Why use the 2 pi AT?
This form? No, I don't need to use this. I'm only using this because I have the F here, but I could have used this formula.
Yes.
The problem is I don't know the omega, but omega is 2 pi over t. So, you see that is there. I don't need to do this, Louise. I'm only doing this because I have the number convenient to me. That's all. Because, F is 1 over t, so I just changed that to F. I don't need to do that. I'm just doing it because it's easier to type on the calculator. Okay. Can I go to the next part? The next part is, what is the acceleration? So the formula for acceleration is omega squared x, and they give me the x here. Okay. Now I don't know the omega, but I know that it's 2 pi over t squared x. Right, so I'll need to type that in. What was my t? What was my t? What was it? My t was 0.476, yeah. Squared, and the x, 0.95 times 10 to the power of minus 2. So I get here 1.66 meters per second squared. And finally, what's the time taken for the mass to move from that position to that position? Okay, so this is a little bit messy. So you have it here, and here's the equilibrium, and it moves from this position, which is 2.0 times 10 to the minus 2, and it goes up to the same distance above. Yeah, sorry, let me try and draw that again. So what happens here is it starts here, and then it goes up to here, and then of course it'll go back down and back up and back down. But both of these distances are 2 times 10 to the minus 2 meters. What's the amplitude? The amplitude is a little bit bigger. It's 2.56. So really, what you could do is you could work out the time it takes to go from the equilibrium to this position, and then multiply the answer by 2, because it does it twice. So you need to use this formula, which I think is in the book. The formula is x equals a sine omega t, where this is the x here. So you would have 2 times 10 to the minus 2 equals a, which is 2.56 times 10 to the minus 2 sine omega t. So you could get 2 over 2.56 equals sine omega t. So we can then do sine inverse. It's not. It's not in the book.
It is.
Oh, it is in the book. Okay, good. So you would get 0.704 equals omega t. So then the t would equal 0.704 over omega. But what's omega? 2 pi over t. So the final answer will be t equals 0.704 over 2 pi multiplied by t. But remember I said that's the time just for half the journey. We multiply this by 2. Well, if I bring the 2 up here, I have my answer. So my answer is 0.704 divided by pi multiplied t. Okay. What was my big T earlier? 0. Are you sure? It's 476, thank you. So I get a time of 0.107 seconds. That was quite a bit difficult, that part. Okay. So now on to the C part. Can I go down? Yeah. C part. So you have light, here it comes, there's its frequency. Frequency is 7.32 times 10 to the 13 hertz. And it shines on some hydrogen bromide gas. What's bromide? Br, is it?
Yes.
And it's found that the frequency is absorbed and is in a resonance frequency of the HBr bond. So what happens is this comes in and then it causes this to vibrate. And, well, firstly, what is meant by resonant? The natural frequency at which the atoms are vibrating at. You know what I hope you remember from chemistry and from physics, that all the atoms inside of a solid, liquid or gas are vibrating. They're not stationary, they're vibrating. Yeah. And when you think about something like ice, are they vibrating faster or slower? Slower. And then the gas? faster. So the resonance frequency is just the frequency these atoms are vibrating at. I think it can be quite different for different materials. So for some materials it could be a small number, like 1 or 2 hertz. And for other materials it might be a large number.
What's the difference between resonance frequency and resonance?
Resonance is the name of the phenomenon. That means one thing will start to vibrate if you vibrate at the same frequency. This is resonance. Resonance frequency is the frequency you need to vibrate at. So the difference would be like the difference between driving a car and a car. So resonance is the process. This vibrates and then this vibrates too. Resonance frequency is the frequency you need to make it vibrate. So in fact, the answer is it's the frequency at which the atoms are vibrating at. That's resonant. Resonance, I keep saying these words so much. That's the process. That's what you have in semester 1 exam.
Okay.
Yeah. Okay. Can I do the second part? Yeah. Okay. It is assumed that the bromine atoms remain stationary and the hydrogen vibrates. Determine the constant. Interesting, very interesting. So what they're saying here is, you need to imagine the picture like this, that the bromide is stationary, and in fact it's the hydrogen atom that's vibrating back and forth around the bromide. Okay? So that's how they say you should picture it. So they're saying picture it like there's a spring here, and it's going back and forth like this. So the question is, what is the K? The only thing you know is the F. They give you the F here. Okay, so let's write down the formulas we know and see if there's one useful to us. We know that T equals 2 pi. Well, you know what? Yeah, we know that T equals 2 pi root m over k. And we know that T equals 1 over f. Yeah? So in fact, I think I can put these together to get the formula for k. So you can have 1 over f equals 2 pi root m over k. So f equals 1 over 2 pi root k over m. So that means f squared equals 1 over 4 pi squared k over m. So that means k equals it equals to it's equal to 4 pi squared f squared. Now the only problem is, do we know the mass? So they talk about relative atomic mass of hydrogen.
I use 1
That's what I'm thinking. Because you don't really care about the mass of the bromide, because that's just like the thing that holds the spring, like the person's hand. And it's the mass of the thing that's moving that you care about. And you're right too. They say that it's 1. Well, not 1 kilogram, of course, but 1 atomic mass unit, 1 U. So here the K would equal 4 pi squared times 1 atomic mass unit, which is 1 U on the calculator, and then the frequency is 7.32 times 10 to the 13 squared. What number is my U? 17. Hold on, I'll tell you now. What did you get?
300.
Yeah, 351 newtons per meter. That's okay. So the question wasn't awfully difficult. There was a couple of difficult parts, like part 6, and, you know, this part here at the end. But mostly I thought it was a good question. Okay, so what's next?